Lesson number 8 is about continuity, differentiability, and something that ties in with both of these ideas called the intermediate value theorem. So before I get started, the notes can be found right over here. So if you click on them, it'll open up into a link that looks like the following. So I will try to keep this as short as possible, but at the same time, I got to make sure that I go through the important concepts that are tested on the AP exam. Now, as it is, this topic is frequently asked about on the AP exam. As you can see, there's 8 pages of questions that I was able to find. But thankfully, the questions that they ask are generally quite straightforward, and it's usually the same kind of question that's asked pretty much every single year. So as I go through this topic, I'll be addressing some of these questions as well. Okay, so let's go ahead and get started. So the first thing that we want to talk about is continuity, right? So continuity is something that we've actually discussed in length when we were in pre-calculus. So it's not anything new, but there's a slightly different take on it when it comes to calculus, all right? So basically, if something is not a broken graph, then it is considered to be a continuous graph. So as long as it doesn't have any breaks, you have basically a continuous graph. All right, so continuous doesn't have any breaks. And so obviously, if something is discontinuous, then it's going to be having some part of it that's broken. All right. Next, we have to have 3 conditions to be met in order for us to call something continuous. Now, most of these conditions can be understood if you simply look at a picture, right? So as I talk about these, I'm just going to draw for you a quick little graph here. Let's suppose that you had a graph of a function, and that function looks like the following, all right? And let's take a point C on this graph, all right? And so then its function value will be called the f of c, like that, all right? So basically, to prove that this point is a continuous point, meaning there are no breaks at point C, we have to do 3 things in calculus, all right? The number one thing that we need to do is we need to find the f of c, all right? We need to find the f of c. So this right here is called the definition of continuity. In the end, it's really what you need to memorize. But what I do here is I break this down for you one step at a time. So when we say find the y value of the function, that would simply be f of c. Okay. Step 2. Then what you do is basically calculus-based, where you find the limit of that function as x goes to c. Now, recall from our initial lesson on limits, which was all the way in lesson number 2, which is the first lesson that we learned, a limit is basically approached from 2 sections of the graph, the left-hand limit and the right-hand limit. And notice that in this situation, if you approach from the right-hand side, this would be the right-hand side over here, of C, you end up with the answer f of c. And if you were to approach this from the left-hand side, now what's the left-hand side? The left-hand side would be over here, to the left hand of C. And if you approach C from the left-hand side, you end up with the same exact y value, right? And so what was the conclusion we used to reach? We used to say if this occurs, then the overall limit, which is referred to as limit as x goes to c, not with a positive or a negative, but just x goes to c, is equal to f of c, right? So whenever we notice that this condition is met, notice that we have actually just proven continuity, because that's what the definition of continuity says. It says that the function value, which was step number 1, needs to be the same as the limit value. So there you go. That's all you need to prove and show in order to show continuity. So if you're wondering what is step number 3 then, and step number 3 is essentially telling you exactly that. It says just check if the function is continuous by making sure that what you got in step 1 and what you got in step 2 are actually the same exact values. So these can be numerical values. So if this c was the number 5, then we'd be talking about the function at 5 itself. All right, so that's continuity in calculus. And how is it slightly different than what you learned in pre-calc? Is in pre-calc you didn't necessarily know what limits were, right, up until the end. So this is why it's a little bit different. And so you just need to check the limit at that point, and that's essentially it. And what we learn is checking that limit, if you can just go ahead and break it into 2 pieces the way that I did, and make sure that they both equal the same thing, you're automatically checking for continuity, because in the red box here, I have shown you the definition of continuity. Now, so what are some things that are not continuous? So these are 4 types of discontinuities. So in these situations, the function is actually not considered to be continuous. So the first type of discontinuity is called a point discontinuity. Now in a point discontinuity, what essentially happens is you'll notice that there is a hole in the graph. Okay, so there's a hole right there in the graph. This is called a point discontinuity. Make sure that you memorize this word, point discontinuity, because the AP exam does ask it specifically, what type of discontinuity is it, all right? And so if you look at the one that's right next to it, it's called a removable discontinuity. So it's quite similar to a point discontinuity, except the hole is made up for. Okay, so notice how there is a closed function right there. So there's an actual defined value. In other words, f of 2 is equal to 4, whereas in a point discontinuity, f of 2 was actually undefined, right? So that's the big difference between a point and a removable. In a removable, it's almost like you removed a part of the graph and then put it somewhere else. And that's essentially what's happening there. Okay, so these are called point and removable discontinuities. And just a quick reminder, in pre-calculus, when we learned these, we did not distinguish between a point and a removable. We simply used to say this is a hole in the graph. Okay, and we'll go over what exactly causes a hole in the graph again as we learned them last year. Okay. All right, let's talk about number 3 and number 4, and then we'll kind of review them a little bit too. Number 3 is called an infinite discontinuity. In a infinite discontinuity, what we used to call in pre-calculus was actually a vertical asymptote. In fact, in some textbooks, they call this a essential discontinuity. So it really has like 3 names to it. And where specifically is it happening? It's this green line that you see here that I'm shading over in red now. But basically that is where the infinite discontinuity is. And so you'll notice that the graph is going to be splitting up into 2 different parts. And finally, the last kind of discontinuity that we have is called a jump discontinuity. And basically what you'll notice is you'll be coming along in a graph, right? You'll be coming along in a graph, and then all of a sudden what happens is there's a bit of a jump in the graph, and then you continue onwards. So that is called a jump discontinuity, and it's quite distinct from the other types of discontinuities, so it's hard to miss. So again, to recap, we now know what a continuous function is and what the definition of continuity here is. But then there are some types of discontinuities, and the 4 that you need to know are called point, removable, infinite, and jump. Okay, now we're going to run through an example that we have done similarly for an example in lesson number 2, back when we were learning limits. But this time, because we're talking about continuity, we're sort of revisiting this same exact example. And part of the reason why we learn it so far apart is because that limit taking process takes some time to understand. So we don't talk about continuity right then and there. We talk about it way later. So now what happens is you have a couple of graphs in front of you. And in this first graph, again, hopefully this is going to ring a bell for you. In this first graph that you see on the top left-hand side, notice that the function of 4 is equal to 4. So if you were wondering what is the y value at 4, the y value at 4 would be this number right here, 4, right? So it's not 2. Be careful of that because there is a open circle at 2, so that's not the y value there. Now, if you look for the limits from the left-hand side, the left-hand side limit as you're approaching this from the left-hand side is actually equal to 4. And if you're approaching 4 from the right-hand side, well, that would actually equal to 2, right? And so in that situation, notice how the left-hand side limit and the right-hand side limit are not the same. And so that generally is enough for you to say, well, then they're going to be discontinuous. And back in lesson number 2, we used to say does not exist as far as the limit is concerned. But how do you say this in terms of the definition of continuity? Basically, you begin by writing down by saying that the function at 4, which by the way does exist, it's equal to 4. We saw that over here, right? So the function at 4 is not equal. So it's not equal to the limit as x goes to 4, right? We noticed that when we tried finding the limit as x goes to 4, it ended up being two separate numbers. So in other words, the overall limit did not exist. And so this is our reasoning, and I've put it in bold letters for you because it's important that you're able to write this in terms of the definition of continuity. So whenever you hear it says write in terms of definition of continuity, you need to write it like this over here, okay? And so we conclude that the function is not going to be continuous at x equals 4. Just while we're looking at it, what type of discontinuity is this specifically? This is called a jump discontinuity because notice that the graph was just coming along and then it literally just sort of jumps downwards and then it continues onwards. Okay? Now while we're looking at things, let's take a look at the graph on the right really quickly. The function at 4 is actually undefined, right? Notice how there is an open circle at 4, but it's not made up for anywhere, so it's actually undefined. Whereas the limit, if you find the limit from the left-hand and the right-hand side, you'll notice that the limit does exist, right? So as you approach 4 from the left-hand and the right-hand side, the limit does exist, and the answer is actually equal to 4. So this works out for us, right? Now, what's the problem? Why do we call this discontinuous? We know it's called a point discontinuity, but why do we call it a point discontinuity? Again, the answer lies in us talking about the definition of continuity not working out for us. What exactly happened here is notice that the function at 4, which is undefined, is not equal to the limit as x goes to 4, right? The limit as x goes to 4 was 4, but the function is undefined. And so since those two are not the same, we once again conclude that it is discontinuous there. All right, let's take a look at this a third time really quickly. In this graph over here, notice that the function at 4 is equal to 4. All right, it's not 4 comma 3. Be careful of this. Many students have made this mistake in the past. This is 3, this is 4. There is an open circle when the 3 occurs. In other words, the function at 4 is not equal to 3. It's actually equal to 4, where the closed circle is. All right, so that's point number 1 to make. Point number 2, as we try to find the limit as x goes to 4 from the left and the right-hand sides, we notice that the limit does exist, and that is equal to 3, right? Because both of these numbers are actually the same. Well, when this situation happens, what's the matter here? Again, this is a removable discontinuity, but how do we justify it? We once again mention this statement. And what we're saying is the function at 4 was actually equal to 4, but the limit as x went to 4 was actually equal to 3. Now 4 is not equal to 3, and therefore there's a discontinuity. So moral of the story is if you can prove that this side is equal to that side, meaning the function is equal to the limit, the pre-calc is equal to the calc, then this is a continuous function. Otherwise, it's a discontinuous function. Now, many students ask, do we really need to know this over here? You keep talking about the definition of continuity. Is this so important? Do we really need to memorize the way that it's written and stuff like that? And yes, absolutely. You need to know the definition of continuity. So make sure that you spend some time memorizing it and understanding more so what it actually means. Now what I want to do is take a moment and pause the calculus for a little bit and talk about something that we did in pre-calc. This is exactly the same thing out of a pre-calculus book, all right? So in this, what we're going to do is we're going to find a few things. Number one, we're going to find point discontinuities. Number two, we're going to find infinite discontinuities. And number three, we're going to find horizontal asymptotes, all right? So I know that we never called it a point discontinuity. We actually used to call it a hole in the graph. I know we never called it an infinite discontinuity, but we did call it a vertical asymptote of the graph. And finally, there's horizontal asymptotes, which we did call exactly the same thing in pre-calculus. So let's go ahead and get started. I have a rational function, so these are called rational functions. F of x is equal to 2x squared minus 5x plus 2, and it's divided by x squared minus 4. So one of the first things that you want to do with it is you want to go ahead and factorize the rational function. So what you see below it is basically its factorized version of the same exact function. Now notice a few things about this factorized version is there is a factor that says x minus 2, and there's another factor that says x minus 2. And we learned something about this in pre-calculus, right? We learned something about this in pre-calculus, and what we essentially learned is you can actually cancel out the x minus 2's. And if you cancel them out, basically what you're left over with is this over here. Now, based upon that, you can now make two conclusions. The first conclusion that you can make is because the x minus 2 factors actually canceled out, what you can therefore do is take x minus 2, equal it to 0, and then solve it, and conclude that there is a point discontinuity on the graph, meaning there is a hole in the graph at x is equal to 2. And I will show you a picture of this in just a moment, but that's the part you need to believe, that there is going to be a hole in that graph at x equals 2. And the factor that remains, so what remains in the denominator, right, not the numerator, but in the denominator, which is an x plus 2, well, what you basically do with that is exactly the same thing. You set it equal to 0. And when you solve it, you end up with x equals negative 2. And what you end up with is called a vertical asymptote. All right, it's called a vertical asymptote. But in this course, and please do remember these names, it's called an infinite discontinuity. So I've pulled out a picture of this graph, and I'll come to the horizontal asymptotes in just a moment. But take a look at a couple of the qualities of this graph, right? Notice that at x equals negative 2, it does have a vertical asymptote, but we call these infinite discontinuities. And at x is equal to positive 2, notice that it has a hole in the graph there. You see that? Okay, let's finally talk about the horizontal asymptote. How exactly do you tell a horizontal asymptote? Well, first off, we learned in lesson number 2, and then we repeated this later on in another lesson, is a horizontal asymptote can be called a horizontal asymptote even in calculus, but what it really stands for is the limit as x goes to infinity, right? And so where have you learned infinite limits and all of that stuff? You learned limits going to infinity in the lesson right before it that we did learn together. So we skipped lesson 8, but we never skipped lesson 7. So if you need to review your graphing rational functions, you're welcome to click on this link and go to the lesson about reviewing rational functions, which is lesson number 10. And it's even got pre-recordings and everything. And it's got the properties and graphs and stuff like that, just in case you have forgotten anything about it, right? So anywho, back to what we were talking about. What we want to do is we want to go ahead and find the horizontal asymptote. Now, how exactly is this done? Basically, what you do is you look at the degree of the numerator and the denominator, right? So you look at the highest degree in the numerator and you look at the highest degree in the denominator. Now, notice that the highest degree in the top is a 2 and a highest degree in the bottom is also a 2. And so this is the case of same degrees. And what we learned is when you basically find that they have the same exact degrees, you pull off the leading coefficients of those particular higher powers. And so in this situation, that would be a 2 and a 1 that you're going to pull off. All right? And so you end up with a horizontal asymptote of y equals 2. So again, if you're getting confused by what's going on here, so this is calculus and this is pre-calculus. In pre-calc, we had a little trick that we used to do, right? And then in calculus, we actually learned a way to take a formal limit, but basically the process is exactly the same. You don't have to use L'Hopital's rule necessarily here. You just simply need to come to the conclusion that in the end of the day, you're going to end up with an answer of 2 over 1. If you do decide to use L'Hopital's rule, by the way, I'm not stopping you, because initially you do end up with infinity over infinity. But if you were to take the derivatives, right, limit x goes to infinity, the derivative of the top would be 4x minus 5, and the derivative of the bottom would be 2x. Notice how this again would lead to infinity over infinity. So you can go ahead and take another derivative, but see how this is taking unnecessarily longer than we really wanted to. The derivative of the top is 4, and the derivative of the bottom is 2. 4 divided by 2 gives you 2. So that is saying exactly the same thing as what the horizontal asymptote was saying. So it's just in our better interest to understand that and then stick to, the easier way of telling a horizontal asymptote. Okay, but keep in mind that a horizontal asymptote, which now is right over here, is known as a limit as x goes to infinity. And in calculus still, it's still called a horizontal asymptote. All right. Now, what we're going to do is take a look at a few of the points on this graph here that was above and just makes a few conclusions about whether something is continuous there or not continuous there. And part of the reason why we do example 2b is just to familiarize yourself again with something that tends to bother students a lot, which is the definition of continuity. They really struggle with the idea of talking about the definition of continuity. So I have shown you it 3 times. And so let's go ahead and consider 3 numbers, okay? -2, 0, and 2, all right? All right, let's start with x equals -2. Notice that when x is equal to -2, if we were to go to the graph, what's happening at x equals -2? There is basically a vertical asymptote. Now, why do we have a vertical asymptote? What's going on there? Well, notice that from the left-hand side, the limit shoots up to infinity. From the right-hand side, the limit goes to negative infinity. And so obviously the limit doesn't even exist at -2. But beyond that, notice how, because it's a vertical asymptote, the function at -2 is also going to be undefined. So you have all kinds of problems happening at -2. So what do we conclude as far as the definition of continuity is concerned? We say, well, the limit from one side is positive infinity. The limit from a different side is negative infinity. So the overall limit doesn't even exist. And that is, sufficient. But if you look at the fact that the function is undefined at -2, that's all the more reason to say it is discontinuous at x equals -2 because of a infinite discontinuity, like that. All right, let's take a look at the next one. What if we were looking at x equals 0, right? So I purposefully picked one that actually works for us. So take a look at x equals 0. First, let me just kind of clear out some of this clutter here. So let's take a look at x equals 0, right? Now at x equals 0, it says that the y value when x is 0 is equal to -1/2. So we notice that f of 0 is equal to -1/2. But beyond that, notice that if you were traveling towards 0 from either end, there is no problems with that. You would actually end up with a valid limit. From either side of 0, you would notice that the limit is also equal to -1/2. Now notice how these two answers are actually the same. Because these answers are the same, you cannot say this is discontinuous. In fact, the answer is it is continuous, right? And then by the same token, if you take a look at the function at 2, right? Take a look at the function at 2 and take a note at the take a look at the limits at 2. Let me see if I can fit this in here. Here is 2 over here. Now, as you take a look at the function at 2, there's a hole there, so you know that's going to be undefined. And if you take a look at the limits, well, the limits actually work out for you. When you're coming to 2, remember, open circles don't cause any problems for us. So the limit actually exists at 2. That's not an issue. This is a perfectly good answer. 3/4, right? It says 3/4 over here. So that's not the problem. The problem is the fact that you have an undefined function, right? So what we say is when x is equal to 2, the function value there is not equal to the limit value there because the function is undefined and the limit is equal to 0.75. Now those two are not matching. And because of that, we say that it is discontinuous. But beyond that, we also conclude that this is a point discontinuity. Okay, so I have several such examples just to kind of be able to tell continuity. And in the past, what I've generally done is I've asked students to actually read these by themselves. They're quite self-explanatory, right? Just read example number 3 by yourself and make sure that you know how to show basically discontinuity or continuity by showing limits and then showing a function's value. So example number 3 is like that. Example number 4 is the same. Remember to show your work when you're going through these, all right? And I've even gotten graphs and stuff like that for you. Now, what I want to spend my time on is an AP question, which is example number 5, okay? So this is a very popular question on the AP exam, and if you're in a bit of a hurry, these are the types of examples that you want to basically learn, even if you haven't been able to completely wrap your mind around continuity. Okay, so this one is very, very important for you to know. All right, so it says find the constant a such that the function f of x is equal to x squared as long as x is less than or equal to 2. So what's going on here? So as long as x is a number that's less than or equal to 2, we're saying that the function is equal to x squared. But as soon as the number is beyond 2, right? So anything that is beyond 2 is going to be ax cubed, right? That's what the piecewise function right over here is trying to communicate to us. So it says, can you make it such that a would be some number that would cause this function to be continuous everywhere? Now, let's again revisit the idea of continuity. If something is continuous, it's not broken. And if it's not broken, that means the definition of continuity, which is right over here, needs to hold. So how exactly does this apply? Well, step number 1, let's find the function at 2. Right? Let's find the function at 2. So what we do is we go to this piecewise function and notice that the piecewise function says that if x is a value less than or equal to 2, then you plug into x squared. If x was any value greater than 2, then you would plug into ax cubed. Because they are asking us for the x value of 2, we're going to plug into the top equation. So when we plug into the top equation, we end up with an answer for f of 2, and we know that the f of 2 is equal to 4 because 2 squared is 4. Then we have to find the left-hand limit and the right-hand limit. Now again, if you're wondering why would you need to do that, it's because that's what the definition of continuity asks us to do. It says find the overall limit, and we know that for an overall limit to exist, the left and the right-hand sides need to be exactly the same. So how do you exactly do this in a piecewise function? It's actually a lot easier than you might imagine. All you need to do is you need to plug in the value x is equal to 2 into both sides. Now, a lot of students ask, they say, wait a minute, I thought we were only supposed to plug x equals 2 into the top function. Yeah, that's when you need to find the function at 2, and we did that already. But this second piece over here, condition number 2, this was condition number 1. Condition number 2, it's asking you for a limit, you understand? So when it comes to a limit, you're allowed to plug the number even into a domain that's not allowing it, right? So we're going to go ahead and plug the number 2 into the left-hand side and into the right-hand side. So what does that exactly look like? Well, when we plug it into the left-hand side, it becomes 2 squared as it was before. And when we plug it into the right-hand side, notice how the right-hand side said f of x is equal to ax cubed. So when we plug in f of 2, that simply becomes a times 2 cubed, which is simply 8a. And that's what you're looking at right over here. All right, so there's the 8a. And so if you solve this, you end up with a value of a is equal to 1/2. So if you're wondering, that's a pretty weird question and the way it's worded. So this is generally on the AP exam every year. And this is usually how they test about continuity. At least one of the questions that they test on continuity. But it's pretty much an every single year question. It's quite easy to actually do. All you need to do is essentially take the number that's been written here and just plug it into both functions and just solve for the unknown. That's all it really stands for. Okay, now if you're wondering what exactly would that look like, right? Like what did we just do there? And so I've got a little graph for you here to kind of understand and appreciate what really happened. Is notice that if this over here is x is equal to 2, all of the function that is before x is equal to 2 is actually the square function, right? F of x is equal to x squared. That's actually the square function over here. And what I did is notice that they had said that anything that was beyond 2, was a different graph altogether, and that graph was f of x is equal to a x cubed. So if you just found out that a is equal to 1/2 x cubed, this is basically the graph of 1/2 x cubed. And notice that at the point that I've got 2 arrows, notice how you can barely tell that there is any kind of a problem in that graph. And so it looks like a very connected sort of graph. So that's all the question was saying is what should we make the value of a such that the two graphs would actually connect? Okay, just in case you're wondering, what did we just kind of figure out there? Okay, let's try another one. It says that, and this is very similar. Usually I would pause and ask you to try this one by yourself. It says, now can you find another constant a so that these two functions are actually equal? Now, if you want to pause and try it yourself, that's perfectly fine. You're welcome to do so. And so, again, step number 1 is I'm going to find f of 1. And when I find f of 1, remember that's to plug into the top because it says that x can equal 1 for the top, but it cannot equal 1 for the bottom. So I plug in the number 1, and I end up with 3. Then in step number 2, I'm going to basically plug the number 1 into both sides of the function, into 3x cubed and in ax plus 5. And when I do that, you end up with an equation that looks like this over here. And when you solve for a, you end up with -2. Again, if you would just like to appreciate what does that exactly do for us, well, essentially what has happened is you have this function right here that is going to be 3x cubed, and this function right here, which is -2x plus 5. Both of these are functions that you have learned in pre-calculus. But notice that the two functions are connected. And because they are connected, now this function is a continuous function. So that's what was so special about finding what a was equal to. All right, now at this point, generally, I would have pause and have you complete a practice problem set. So in class, I will have given you more instructions about what to do if you're supposed to be finishing this problem set or not, because we're on a different sort of schedule during these times. So more details on set number 1 in class. Okay, now what we're going to do is we're going to talk about differentiability. So much of this conversation about differentiability is going to sound an awful lot like continuity. Okay, so feel free to pause, go back, and rediscover what is continuity. But I do touch on the differences as I continue to talk about differentiability. Now, first off, now you've been hearing this word since day 1 in this class, right? And what exactly does differentiability mean? If something is differentiable, you can find a derivative there. But we have learned about 3 cases, right? 1, 2, and 3, where you cannot find derivatives, and they have various different kinds of problems. So a corner is a problem for us because basically if you were trying to find a derivative at the point 0, you wouldn't know which side to take the slope of, the left side, which is actually a negative slope, or the right side, which is actually a positive slope. So because there is an ambiguity, because there's a disagreement, you cannot take a derivative exactly at 0. What I want you to notice, though, is the function is still continuous, meaning it is continuous, but it's just not differentiable. You get it, right? So let's take a look at another example. In this case, again, same problem exists. At x is equal to 0, there is something called a cusp, right? There's something called a cusp. And beyond that, though, is notice how it is still continuous. So be careful. When we say differentiability and we say continuity, it is possible to be not differentiable. So these are cases where it's not differentiable, but it is still continuous. All right? So they're not exactly interchangeable as some people think. And finally, number 3 is a vertical tangent. In vertical tangent, basically what happens is right over here, let me pick a different color, right over here at x equals 0, just for a moment in time, the slope actually becomes undefined, all right, because it shoots up, literally up like that. Now I'm exaggerating that part right there, but because that happens, the slope is undefined, so the derivative is undefined there as well, because slopes and derivatives are basically the same thing. So one thing I will mention for a third time is still continuous there. So this becomes quite interesting because what you realize is it's possible to be continuous yet not be differentiable at the same time. Well, then what begs the question is, what about all that stuff that we talked about before? How does that tie in with everything now? Well, it turns out the 4 types of discontinuities automatically, all right, these 4 types that we talked about. Now, what are the 4 types that we talked about? We talked about a point, we talked about a infinite, we talked about a removable, and we talked about a jump. So all 4 of these are also points along the way that are also considered to be not differentiable. So altogether, you actually have 7 cases where something would not be differentiable. All right? The 3 top cases, why have they been written so separately? It's because you want to realize is they're not differentiable, but they are still continuous there. Right? They are still continuous at those points over here. However, every point where you are discontinuous, you're automatically also not going to be differentiable. Because if you just give it some thought, how can you possibly take a derivative at those given points where so many problems already exist? All right. So again, an implication of this is if a function is then differentiable, if you've been told that something is differentiable, well, automatically, you're going to have to conclude that it must also be continuous. You just want to pause and think about that for a second and I agree that actually that would work, right? But here is the one that's often misunderstood by students. If you've been told that a function is continuous, then it does not always mean that it's differentiable, because we learned that there are three cases where you could still be continuous, but you're not differentiable there. Okay, so implication one, you hear differentiable. Differentiable is a stronger word. It automatically implies that something is continuous. But if you hear something is continuous, it doesn't necessarily imply that it's differentiable. You need to have further more information. Okay, so what I've got for you here is a very quick diagram for you to take a look at. And on the right side, I've told you what exactly is the problem with different points along the diagram. All right, so here is a graph of f. Now notice that the first interesting point to us would be A, right? Let's take a look at point A. And so what would you have said before this lesson? You would have said that at point A there is a corner or a cusp, right? So what we can say at point A is it is still continuous, but it's not differentiable, right? It is still connected, but you cannot take a derivative there. All right, let's take a look at point B. Now at point B, what is occurring? This is called a removable discontinuity, but beyond that, it's not continuous, and automatically, because it's not continuous, it's also not differentiable, like that. All right, let's keep moving. Let's go to point C here. On point C, notice that it doesn't have a corner, it doesn't have a cusp, it's all connected. So in fact, at point C, it is continuous and it is differentiable. Both of those things actually check out. All right, let's take a look at point D. Now, clearly at point D, this is a discontinuity, that is a jump discontinuity. And so same exact as point B, it is not continuous and it's also not differentiable. All right. And finally, if you take a look at point E, there is no problems at point E. It's clearly nice and smooth, so you can take a derivative there. And so it's also going to be continuous there as well. Okay. Again, at this point, you would have generally had another homework to do. So more instructions on that in class. I really can't tell right now what's going to happen here. Okay. All right, just a quick little comment to make is a common mistake students have made in the past, right? So if somebody tells you that a function is differentiable, it doesn't necessarily mean that its derivative is also differentiable, all right? So is a common mistake students think is, all right, now notice I'm not talking about differentiability and continuity. I'm saying if somebody tells you that a function is going to have a derivative, that doesn't mean that the graph of its derivative will also be something you can take derivatives of. It's not necessarily true. Okay? So I wanted to make that little point as we move along. Now, I want to kind of summarize a few things here about continuity and differentiability. Okay, so you can find this in the formula sheet as well. All right, you can find this in the formula sheet. And because this is a popular question on the AP exam, I wanted to make a point to just kind of recap everything that we've learned about continuity and differentiability. Okay, so number one, if you've been told that a function is differentiable, then it's also continuous. All right. However, if you've been told that something is continuous, it isn't necessarily going to be differentiable. Now, what is the definition of continuity? It is right over here. And it, again, has certain meanings to it. It's a three-step process. Go back and review it. And if you have a piecewise function and you have to work with continuity, basically this is the secret. Just take the left hand and the right hand and equal them to one another, and you're in business. All right? Let's take a look at this right side column. When somebody tells you something is differentiable, that means its derivative is going to exist. And furthermore, so we're going to look at examples like this in a moment. Let's suppose you had a piecewise function and they talked about differentiability. Well, in that case, what you would do, and this is new to you would actually take the derivatives and you would set those derivatives equal. You would set the left hand and the right hand derivatives equal because that's what it means. If something is differentiable, its derivative is going to exist at a number. So the same way that you set the functions equal to one another in continuity, you set the derivatives equal to one another in differentiability. So I have written this over here for you, derivative and function, so you know what are you supposed to equal to what, all right? And so we're going to talk about that in a moment and give you some examples to kind of go through. And one more thing to just kind of talk about is two important types of discontinuities. Now, I taught you 4 discontinuities here: point, removable, jump, and infinite. But the two that are recurring, and pretty much every single year they're going to ask you about these two, is the removable, which is essentially a hole in the graph, and then the infinite, which is essentially going to be a vertical asymptote. Okay? All right, now you are welcome to read this part of the lesson by yourself, and I would highly recommend that you do that. But basically, what's happened in the past is students have known the families of functions. They know the families of functions, but when you transform some of those families of functions, it seems like you don't exactly know what those functions are, right? So what I want to do here, just briefly, is talk about, well, how can you look at the equation of a graph, right, without looking at the graph itself? How can you look at the equation and determine if something has a sharp turn or a vertical tangent, right? So a corner or a cusp is also called a sharp turn. Actually, you can use this on the AP and they'll be okay with you calling it a sharp turn as far as corners or cusps are concerned. So let's talk about number 1 here. Just very quickly, the function of x is equal to the absolute value of x. Now, this is something that we learned in pre-calculus, all right? And everybody knows that this is the absolute value family. And in calculus, you realize that the absolute value family at x equals 0 is not differentiable because it's got a corner there or a sharp turn there. Well, what if you had the equation f of x is equal to x minus 4? Can you, absolute value of x minus 4, can you think back to transformations and how things are moved around a graph and figure out what might that graph look like? Okay, so if you're thinking to yourself, does that mean it's shifted to the right? That's precisely what it is. It's actually the absolute value family shifted to the right, but a lot of students don't tend to remember that when it comes to the AP exam because it's been so long ago. So one thing that you can do to kind of prevent yourself from forgetting is basically the absolute value of any linear function. It's always going to contain a corner. So if you notice that you have an absolute value and the function is linear, meaning it has a highest power of x there, it's guaranteed to have a corner in it. And all you need to do to find that corner is you basically need to set the inner function equal to 0. All right, that's the secret. And if you solve it, it'll tell you exactly where that is. So even if you don't know what the graph looks like, just take the inner function, which is x minus 4, set it equal to 0, and it'll tell you where the corner in that graph is. And if you take a look, that's exactly where the corner occurs. Okay, now let's think about something like 2x plus 5 absolute value, right? Now, initially that might seem like, oh my God, what am I supposed to do with that? That's basically something that's shifted to the left, but it's also vertically stretched and stuff like that. Again, you don't have to be an expert with graphs. What you could do is you could just say, well, this is a linear function and it's inside an absolute value. So I know there's going to be a corner, and the place you can find the corner is take the inner function and set it equal to 0. When you do that, you have figured out where the corner is going to be. The corner is at -2.5. So there's your corner right there. You see that? Now, let's talk about a few more interesting cases. Let's suppose that you had an absolute value once again, and it's basically around any function that is second degree or higher. Now, here's the problem. This may contain a cusp. It's not necessary for it to contain a cusp. Why exactly is that? It's because, well, some functions basically never go below the x-axis, and in that case there would be no cusp occurring there. Well, let's take a look at something that does have a cusp occur. Um, take a look at this function right here, x squared minus 3 with an absolute value around it. So notice how this is second degree. And why does it have a cusp? Well, if you take a look at the inside, if you look at the inner part of it, and you set it equal to 0, so it's the same idea as before, but the only difference between step number 1 and number 2 is basically in this one you may contain a sharp turn, but no guarantees. So in this situation, when you take x squared minus 3 and you set it equal to 0 and you solve it, you end up with definitely two answers, right? And now here is the decimal equivalent of it as well. And what happens, the only way I can prove it to you is if I show you the graph, right? What essentially happened is this, right? Again, if you tend to be very good with graphs and you're able to think about them, what it really was is it was actually a parabola. Okay, it was a parabola that had the function x squared minus 3. But when you put an absolute value sign around it, when you put an absolute value sign around x squared minus 3, what it's saying is this part of the graph that is below the x-axis, right? Because these are all negative y values, they can't be negative anymore because you just put absolute value around it. So what happens is that part reflects to the top, and so it looks like this over here. And so that's why you're looking at a graph that kind of looks like a parabola, but it's been flipped up in a weird kind of way. And so using this technique, you can actually tell where, and the AP exam doesn't ask you exactly where the cusps are, but it just helps to kind of know things at such a good level. Right, now notice how this next one, it actually doesn't have a cusp. And why? Is because x squared plus 4 absolute value is the same thing as x squared plus 4 just in regular, because this is never going to become negative. This never becomes negative. And because it never becomes negative, even putting an absolute value around it is never going to give you anything on the inside equaling out to 0. You can try it and you won't end up with anything that's real. So there is no cusp in this graph, right? So before you make the wrong connection that anything that's inside an absolute value must have a cusp, that's not necessarily true, and I'm showing you such a case over here. Okay, I have a few more examples, and please feel free to read them, but x cubed minus 8 with an absolute value, definitely it has a cusp, and you can see that. I think there's a small typo here that's supposed to say x cubed minus 8. Right, x cubed plus 27, very similar, as well as the typo is similar, so x cubed plus 27, that has a cusp as well. All right, now about vertical tangents, well, the third root, okay, now these are the popular ones, okay, so they're not everything, but these are the popular ones. If you notice that there's a function and it's got a third root, it may contain a vertical tangent. Okay, so a vertical tangent is a very unique thing, but you wonder, when have you ever learned this? You actually learned this on the cube root family. The cube root family has a vertical tangent, right? And so the cube root family is shown to you in front. Of course, we've written it in its more common form in calculus, but that right there has a vertical tangent at x equals 0. And notice how you can still do the same thing. If you set the inner function equal to 0 and solve it, you can figure out where that vertical tangent would lie. And so take a look at this second function over here where you have x to the power of 4 plus 1 to the power 1/3. This one has no real solution, right? There is no such number that you could plug in over here that's a real number, and it would cause it to be equal to 0 in the end. So there is no vertical tangent. So just because something has a third root isn't necessarily saying that it's always going to have a vertical tangent. All right. And I've got, several examples, but here is one where you have x to the power of 4 minus 16 to the power 1/3, and just testing it out. We're just testing it out. This is the easiest way to do it. Just take the inner function, set it equal to 0, and notice how this one actually has solutions, meaning it's guaranteed to have vertical tangents. Whereas if you got no solution, right, if you receive no solution, you know it doesn't have vertical tangents. So when in doubt, if you see absolute values, right, or if you see a root, just take the inner part of that absolute value or that root and set it equal to 0 and solve it. And if you end up with an actual answer, then what you can conclude is this thing actually has a vertical tangent, or it has a corner, or whatever it may be. So now what we're going to do is talk a little bit about differentiability and continuity, and try a number of AP questions that basically are going to be tackling both of these generally in the same exact question. And I'll show you how that actually works on the AP exam. But really quickly, one thing to know about this lesson, as I've shown you before, is when it comes to the AP questions, there's quite a lot of predictability in how they're going to be structured. And so as I go through these examples, I will be touching upon that structure and how you're supposed to basically go about this question. Okay, so you don't need to understand everything about differentiability and continuity in order to get these questions correct. And that's kind of, I think, the good news there. All right, so let's go ahead and start. It says that example number 1, find a and b so that f of x is differentiable everywhere. Now here's something that we have learned, and we've learned it multiple times in this lesson, is when you hear that something is differentiable, then it's also going to be continuous. And so if something is differentiable and it's also continuous, that means the derivatives from the left and the right hand side are going to be the same, as well as the functions from the left and the right hand are going to be the same. If that's not ringing a bell for you, if you're like, wait, how do you know that? Well, this is one of the things that we basically discussed in this slide over here, where we talked about what does it mean when we say something is continuous in a piecewise function, and what does it mean when we say something is differentiable in a piecewise function. When they're continuous, you set the functions equal to one another, and when it's differentiable, you set the derivatives equal to one another. But the fact that differentiable is backwards continuous means if you ever hear the word differentiable, you can also assume that the functions are going to be equal to one another. Okay, so how does that exactly apply? This is what I want to discuss in this example and several examples after this as well. So because we were told that you basically have a function that is differentiable, we know that it must also be continuous. All right, so we begin by essentially taking the left hand and the right hand limits, and notice that the number that they are specifically referring to is the number 0. So we're approaching 0 from the left hand side and the right hand side, and we're setting that the two pieces equal to one another. Now, students often ask, what am I supposed to plug into the value of x? You plug in the 0 into the value of x, right? So this is why we end up with sine of 0 is equal to a times 0 plus b. And notice that a times 0 is still 0, and sine of 0 is equal to 0. Therefore, the value of b is equal to 0. Okay, now notice that we know what b is, right? We have figured out that b is equal to 0, but we still haven't figured out what a is. So how exactly are you supposed to go about this? Because technically speaking, we really can't plug in anything now into the functions. So what we do instead is we use the fact that it's also differentiable, right? In fact, that's the word that they had used. So because it's also differentiable, what we do is we take the derivatives of both of these functions, right? And we set them equal to one another. So what are we essentially going to be doing here? This is basically the process. Notice how it looks very similar to the continuity process. The only difference is this is the function, whereas these are the derivatives of those functions. You get it? And so let's go ahead and demonstrate this. The derivative of sine of x is cosine of x, and that's why you have that. And the derivative of ax plus b is simply going to be a. And so now what we'll do is we'll go ahead and we'll set the cosine of x equal to a, and exactly at which value? At the value 0. So notice how I can plug the 0 into the cosine, but I can't really plug the 0 into the a. There is no x's there to begin with. Remember, it's a that you're actually trying to solve for. Anyway, so you end up with cosine of 0 is equal to a, and so when you solve this, you end up with a is equal to 1. So we conclude that the function can be differentiable everywhere if a was equal to 1 and b is equal to 0, meaning you will not have any corners, any cusps, or vertical tangents as long as you make the value of a 1 and the value of b equal to 0. All right, if you want, you can actually pause this video and you can go ahead and try this by yourself. The question says that you have a piecewise function, and these are all from the AP exam basically, all right? So you have a piecewise function here. What you need to do is, number one, show that f is continuous at x equals 0. And then number two, you need to show that f is actually not differentiable at x equals 0. Okay, so it's not differentiable, right? So let's begin with the continuity thing, right? So to show that something is continuous, you need to show that the function at that number is equal to the limit as you approach that number. And what we just learned is when we were talking about the limit of a piecewise function, that essentially means that we need to look at the left-hand side and the right-hand side. So 0, negative f of x, and limit x goes to 0 from the positive side of f of x. So we basically need to make sure that this is equal to this is actually equal to that. So notice how the definition of continuity, as we've learned it, gets a little bit extended, but that's only because we understand that in a piecewise function, an overall limit essentially means the left and the right functions of that particular number. So let's talk about number one first, showing that f is continuous at x equals 0. Then we'll get to number 2. All right, so here's what we're going to do. The first thing that we'll do is we'll find f of 0. All right, so now if you want to find f of 0, that means that we need to plug into the top function, right? So we plug into the top function because notice how the top function says that x can equal 0, and they are interested in where x is equal to 0. So we use the top function to plug a 0 into. All right, now I plug the number 0 in, and f of 0 is equal to 1 minus 2 times sine of 0, which was equal to 1. And so I have figured out what the function at 0 is going to be. All right, so I figured out this piece over here. Now I need to show that the limit is the same on both sides. So how do I exactly do this? Once again, you take the number 0 and you plug it into the top function and into the bottom function. So when we do something like that, here it is. We plug the 0 into the right-hand side, and that happens to be, by the way, the bottom function, the right-hand side of 0. And so we end up with e to the power negative 4x, which becomes e to the power 0. When you plug a 0 in right there, that's simply going to make it into e to the power 0, and e to the power 0 is equal to 1. Okay, now let's go ahead and plug into the left-hand side limit. So remember, this is the left-hand side limit, this is the right-hand side limit, right? Because this one says greater than 0, and well, I shouldn't make that symbol there, that might get confusing. This one says greater than 0, this one says less than 0, right? So you know that on a number line, here is 0, and the left-hand side is over here, the right-hand side is over here. You've been told that 1 minus 2 sine x is the equation of the left-hand side, and e negative 4x is the equation of the right-hand side. So essentially what we're doing is we're taking the number 0 and plugging it into both functions and making sure that the functions are connected there. That's all it is. And so we do that. We plug the number 0 into the x, and when we do that, we end up with 1 minus 2 times sine of 0, and that's basically going to give you the number 1, right? And so notice how the left and the right-hand side limits are both going to be equal to 1. So therefore, we have proven that the overall limit is equal to 1. So now let's review. We noticed that the function at 0 was equal to 1, and we noticed that the limit as x goes to 0 is also equal to 1. And so what we can conclude is the function at 0 is equal to the limit as x goes to 0, and that's equal to 1, meaning it's the same number, and therefore the continuity definition is met. Notice how what you need to really check is making sure that that number is equal. It's not that it's equal to 1, but that whatever you got from both sides was equal. If it was unequal, then it would not be considered continuous. Okay, now let's change our discussion and talk about the differentiability. So when you want to show that it's not differentiable, what you essentially need to begin by doing is taking derivatives of the right-hand side and the left-hand side. So you got to take the derivative of 1 minus 2 sine x, then take the derivative of e negative 4x. Now when you take the derivative of e negative 4x, in case you have forgotten how you work with this, recall that there's a formula that really incorporates the chain rule into it, and it says that the derivative of e to the power of u is equal to eu times u prime. And so this right here is your u, right? You should know that by heart. Now, when we go ahead and we take the derivative of this particular piece, here's what we discover is the derivative of the top function that we had there, 1 minus 2 sine x, becomes negative 2 cosine x. And the derivative of the other function, which was e negative 4x, becomes negative 4 e negative 4x. Now we plug in x equals 0 into both of them, and what you'll discover is when you plug x equals 0 into the top function, you actually end up with negative 2 times 1, which is actually negative 2. When you plug it into the bottom function, right, the bottom derivative function, you end up with a negative 4. Notice how a negative 2 is not equal to a negative 4, meaning the left-hand side limit is not equal to the right-hand side limit. And remember, we're talking about the derivatives here, not the original functions. Well, when this phenomenon occurs, that means that, in fact, these are not differentiable at that particular number, which is x is equal to 0. And so we go ahead and we conclude that since the derivatives are not equal when x is 0, it means that the function isn't actually differentiable at x equals 0. So in other words, it is continuous, but it is not differentiable because the derivatives from either end are not equal. And I just want to take a moment. I feel like it's always worth it to just have a little discussion and have just kind of viewing of what exactly does this function even look like. Well, you can take a look at it over here. I brought in a graph. You'll notice that this is basically that sine function that they were talking about. I think it's at 1 minus 2 sine x. And right at 0, right when x is 0, it switches over to e to the power negative 4x. So if you study this very carefully, and particularly that point right over there, you will notice that there is a bit of a turn, right? There's a bit of a sharp turn in that graph. If you want to say a kink in that graph, you could call it a kink, right? Like, when you have a spring, right? And then the spring has a, like, kind of a kink in it, right? Like that. So whatever you want to call it, a corner, a cusp, the AP exam doesn't really mind, but as long as you kind of notice that, well, basically, there is something there that would cause it to not be differentiable. You understand, right? Please realize that regardless of what you call it, and knowing that it's not differentiable, it is still continuous. Okay, yes, it's got a bit of a sharp turn, but it's not broken. It's not considered to be broken, so you can still continue on this graph as you go through it. Okay, all right, I'd like to pause here and allow you the opportunity to try example 3 by yourself. And remember, these are the examples where if you simply click on the link, it'll take you to a video that shows you how to solve it. All right, so hopefully you paused the video and you tried it by yourself. You do have everything in your pocket to be able to do these correctly by yourself. So it says, let f be the function. Now, first off, notice how this is a piecewise, right? So one thing you very quickly pick up is in piecewise functions, basically, even if you don't technically know everything that's going on, the idea is to set the two sides equal to one another, right? So it says, let f be the function defined above, where c is a constant. So notice how there's a c here, and that's a constant number. It says, what is the value of c, if any, if f is continuous at x equals 2? Now, what did we learn? That when they use the word continuous, then you set the functions equal, right? You set the functions equal to one another. But be careful, don't take any derivatives because it didn't use the word differentiable, so you can't set the derivatives equal to one another. You get it? So let's go ahead and start with this. We take x squared sine of pi x, and we set it equal to x squared plus cx minus 18. Now, when x is equal to 2, what we're going to do is we're going to plug 2 into everything. So this becomes 4 sine of 2 pi is equal to 2 squared, which is 4, plus 2c. Now notice how you're plugging in for the x, right? So 2c minus 18. Now, notice how the sine of 2 pi is actually 0, right? Because that's basically the same thing as 0 degrees. And so what this is going to give you a very simple equation to solve. You end up with 4 minus 18, which is negative 14. And you send negative 14 over to the other side, so it becomes positive 14 is equal to 2c. And you can divide by 2 on both sides and end up with the answer c is equal to 7. You see, so it's very easy to actually apply this on the AP exam, and that's why it's totally worth your time to just, if you're skipped ahead or whatever, just understand the basics about it, and you can easily get this question correct. All right. Now this one's a little bit more challenging. Basically, what's happening in this is they don't technically give you like an equation to solve or anything, but it's really hitting on the conceptual idea of everything that we've talked about so far. Okay, so go ahead and pause the video and see what you can make of this question, and then I will go through it with you. Okay, so it says if the limit as x goes to a of f of x is equal to f of a. Now let's pause here. Right, let's pause here. Does this ring a bell? Right? What is this? In fact, this is the definition of continuity. You see, when all the way at the beginning of this lesson, I said, make sure you memorize it, memorize it, memorize it. And this is precisely why I asked you to memorize it, because sometimes they just go straight to the definition. And so it says, which of the following statements must be true? Meaning, there is no doubt about it. It's got to be true. Well, if it's the definition of continuity, then the only one that would make sense to be true would actually be the letter A. And yes, there is plenty of choices to make you really think hard about whether these are right or not. So you're welcome to look at them and disprove to yourself. And what I do in this video, right, when you click here, what I do in this video is I do show you, I believe, why B, C, D, and E don't work, right? But in this particular video where I'm trying to cover an entire lesson in as close to an hour and a half as possible, I have basically not taken the time to discuss B through E and as to why they're throwouts, all right? Example number 5, go ahead, pause the video, give it a shot. All right, example 5 says, let g be a function so that g of negative 1 is equal to 0 and g of 2 is equal to 5. So one thing that we can do to help you visualize what's happening here is we can make a bit of a graph, right? So what are they telling us? They're saying that on the graph of g, if you were to go to negative 1, the coordinate is negative 1 comma 0. Okay, so what that means is the function g is definitely going through negative 1 comma 0. All right, negative 1 comma 0. Okay, let's keep moving. And then it says that the g of 2 is equal to 5. In other words, this is 2 comma 5. So if you go over to 2, they're telling you that you go through a y value of 5, right? So let me color that in red. So this is 2 comma 5. Okay, so this is all we know about the g function. It says which of the following conditions guarantees, so that's a very strong word, meaning it must work for you, that there is some number x between -1 to 2, meaning there is going to be some number between here all the way to here, so that g of x is equal to 3, right? G of x is equal to 3, meaning the y value equals 3. So where is that number exactly, right? So more on this in a little bit, but basically here's an idea. Let's suppose the graph went like this, right? Let's suppose the graph went like this. Notice how this over here is 0, and that over there is 5. Now just logically think about it. If you traveled from 0 to 5, right? If you traveled from 0 to 5, what could you say as a guarantee to make sure that g of x is equal to 3? Meaning there is some y value that does equal 3. So letter A says g is defined for all x -1 to 2. They're not necessarily going to work for us. Remember, defined means it's got a y value everywhere between -1 and 2. But that doesn't guarantee us that there is going to be some value that's actually equal to 3, all right? If you're wondering, well, can you show me how that wouldn't work? Specifically, let's just suppose, right? So I'm going to disprove some of these answers here, even though it's going to extend the video. Let's suppose that when this graph approaches 3, it has an open circle, and then it continues onwards like that. Now, technically, it's undefined at g of 0. But what if it had a removable discontinuity, and so that open circle right there is actually made up for with a closed circle? Well, guess what? It is defined for all -1 to 2. And if you were to ask, what's the g of 0? The g of 0 is not equal to 3. So I have disproven letter A, right? Letter A doesn't work for us. Okay, let's take a look at letter B, though. Letter B says that if you are told that g is continuous for all -1 to 2 inclusive. Now, let's try to understand what would that look like, right? So if we know for a fact, oops, sorry, I got rid of the axes there. So if we know for a fact that this graph is going to be continuous, right? If it's got to be continuous, that means it's got to keep moving without any breaks, all right? No breaks, no point discontinuities, no removables, no asymptotes, no nothing, right? And so what that means is then you're guaranteed to have some x value so that the y value is equal to 3. So in fact, letter B is correct. Now, letter C, you might be thinking, why is letter C wrong? Well, you can prove it to yourself by just making a quick sketch. You could go up like this, come back down, and then go up like this still, and notice how g of x is equal to 3. Definitely, that happens, but at the same time, it's not always increasing, right? Notice how there is a part of the graph where you're actually decreasing. And so we have disproven that as well, right? And you can take a look at some of the other answer choices, and I personally believe they're just throw out answer choices. If there was anything that was, I think, more confusing, I think it really comes down to A or B. And A is a very tricky answer choice, but in fact, the answer is going to be the letter B, okay? All right, so we're going to close up this lesson with a important discussion about a theorem, and we will come back to this theorem in the next lesson as well. But it's basically mirroring what you just talked about and what we just talked about in number 76, all right? So let's kind of have this little discussion to understand where this theorem comes from, and then I'll read it to you and we'll talk about some of its confusing points as well, all right? So technically this has nothing to do with derivatives. This is all about pre-calc, okay? So let's suppose that you had a value A, and it's matching f of a, right? So what do you have? You have a comma f of a. And the graph is traveling through a comma f of a. And then you have a x value b, and so b travels through f of b. So b and f of b. Now you are accustomed to this when we learned the, taking averages and the average rate of change, f of b minus f of a over b minus a, but it's not necessarily talking about that part. Here is what it's saying. It's saying that as long as the graph is continuous on this interval, as long as it's continuous. Now, once again, what does it mean to be continuous? And why are we talking about this now? It's because we learned that continuity means there is no breaks in the graph. So what the intermediate value theorem says, right, what it says is as long as there are no breaks in the graph, we can be guaranteed, we can be rest assured that there is some point, we don't know exactly where that point is, but there is some point along the way, right? There's some point along the way where there is going to be, let's call a arbitrary point C, and it's going to have a matching um, W there. Okay, it's going to have a matching Y value. If you want to call it f of C, that's perfectly fine, right? So we're guaranteeing ourselves that that actually works. Now, a lot of students say, well, that's kind of common sense. If it's connected, I would have said that myself. So, where is the AP exam going with this? For this, we'll have to try a few questions in the next lesson and be able to distinguish basically where does the intermediate value theorem or where the IVT really applies. I'll tell you this much, a lot of students have been able to get these questions correct without, in fact, we just looked at a question about it right over here, and I did that on purpose. So you realize that, look, even if you don't know the IVT completely, you should still be okay. Yes, there has been more recently on the AP exams where they've distinctly asked about, the IVT, but basically what it says is as long as you are continuous on that interval, right, as long as you're continuous on that interval, then the IVT is stating that somewhere, okay, somewhere in that interval, there is at least one point, and you may call that point C, where basically the graph of the line y equals y equals w crosses this function y equals f of x. Okay, so a lot of confusing way to really state that there is basically some value in this interval a to b, right, such that the function at C is going to be between the function at A and the function at B. And notice this idea of being between the x value, between the y value, that's where we get the idea and the word intermediate from. So it's called the IVT, and it's essentially a pre-calculus idea. It has nothing to do with calculus. The precondition, though, needs to be remembered, and you always have to write it, is we have been told that it's continuous, right? And so then it would actually work for us. So I want to show you a quick example of where this actually applies. And so again, these questions, they don't necessarily, they're not like solving equations or anything. You're just trying to show that a theorem works, right? If that's not ringing a bell for you, let's suppose that I gave you a right triangle, right? Let's suppose I gave you a right triangle, and I said this side is 3, this side is 4, and this side is 5. And I said, show that the Pythagorean theorem works. What would you do? You would say, well, 3 squared, right, plus 4 squared is equal to 5 squared. And then you would go about showing this. So it's like a proof, basically. When you use the IVT, it's basically a proof that you're giving, right? So you're just proving something. And I think that's what kind of makes this confusing, is because a lot of students will look at the question and they'll be like, but what is it really asking me though, right? So it says, show that the IVT actually applies on this function over here on the interval 0 to 1. Now, how do you go about doing this? The first thing that's written here, the first thing that you should note down, and it's not written here, is the precondition. You need to always check the precondition. And notice how this is a graph of a polynomial. And the precondition says that the graph needs to be continuous. So continuity needs to exist, meaning there cannot be any breaks in the graph itself. So if you look at it carefully, there is no breaks in this graph. Again, a polynomial graph is known to be a smooth graph without any breaks. So we're perfectly good on that end, right? Now, what do? You basically are going to show that if A is 0 and B is 1, now where did we get those from? The 0 and the 1 are right here. You need to find the f of 0 and the f of 1. That's all that stands for. Now, you've done this before when it came to the lesson on average rates of change. So when you find the f of 0, you discover that it's negative 1. When you find the f of 1, you discover that it's equal to 2. Now, what do you do with that information? All you basically state is that there must be some point called C on the interval 0 to 1, meaning somewhere in the interval 0 to 1, meaning from over here to over here, there must be some number, right? There must be some number on the x-axis, wherever it may be. There must be some number on the x-axis, or not on the x-axis, but basically on this graph between 0 and 1. And basically what you'll notice is that number's y value is going to be between negative 1 and positive 2, meaning it's going to be between this over here and this over here. It's got to be somewhere contained here. And so notice how there's many points that would fulfill this. Like for instance, where my arrow is pointing, if I were to pick this point over here, notice that the value of C is approximately 0.5. And notice that at C is equal to 0.5, at C is equal to 0.5, what do we notice about f of C? It's approximately equal to 0. And the number 0 is between negative 1 and positive 2, right? That's all we're trying to show is the IVT does work, right? It actually does apply and it does work in a graph such as this, okay? Again, this isn't complete discussion about the IVT. We're going to talk more about this in the next section when we detail something called the MVT. But for now, this is just an introduction to what the IVT actually stands for. Okay, this last page of the notes is basically 2 or 3 questions that I would like for you to try. And they're from older AP exams, but they're quite useful and helpful in understanding it. And you'll even notice that some of these questions are very similar to things that we've detailed earlier in this lesson as well. All right.